Now we talked about back propagation through time. To make it simple, we consider an unbiased recurrent neural network. With that, I mean we don't have the bias vector BH. Also, the activation function is just an identity mapping. At time step t, we consider one single example or instance. The instance is xt at time t, and this is a vector with the features. So, following the formula in the previous slide for the hidden state ht at time t, and here we use the lowercase h at time t to indicate the case of a single example. So as we saw before, the hidden state ht at time t get contribution from the input at time t through the weight vector whx, but also gets now contribution from the hidden state at the previous time step h t minus 1 through another width whh. The output layer variable ot at time t. This is a vector with q elements for q categories, and also we use lowercase to indicate the case of the single example. Following the formula in the previous slide, ot, the output layer variable, is equal to wqh times ht. And again, here we don't have the bias vector to make things simple. Now let's have a look at the loss function. We use the lowercase l for the loss function. The loss at time step t is L of OT and YT. OT is output at time step t, and YT is the true value. With the predicted output OT and the true value YT, we know the loss at time t. We take the sum over all the t time steps and then take the average by dividing by t. So that's our loss function L, uppercase L, for all t time steps. This shows the visualization of the network to make it easy for you to visualize. The hidden state H1 time 1. Time step 1 gets contribution from the input H1 at the same time step, and also the contribution from the previous hidden state H0. In the next time step, the hidden state H2 at time step 2 get contribution from the input at the same time step H2, but also contribution from the hidden state from the previous time step, which is H1, and so on. And H3 get contribution from the input H3 at time step 3, and from the previous hidden state H2. The hidden states make up the output The outputs are compared with the true values to get the loss. Now we have seen three types of widths in the model: WHX, WHH, and WQH. WHX is the width between the input and the hidden layer. WHH is the width between the hidden layer at time step t and the previous hidden state. And eventually WQH is the width between the hidden state at time step t and the output. We need to calculate the derivative of the loss function with respect to the widths. Though derivatives are needed in your gradient descent algorithm, we first start with the derivative of the loss function with the output at time t. So here just a reminder, if from the previous slide the loss function is the sum for all the t time steps of individual loss at time t divided by t. So here taking the derivative of the loss L with respect to the output at time t of t. Only the loss at time t matters. So then eventually you have this. We need three derivatives, right? So we start with this. Now I go back to the visualization a little bit. We can see the loss function L depends on the width WQH via the outputs. So here we apply the chain rule to calculate the derivative of the loss with respect to the width WQH. And here we have the sum for all the t time steps of the products of derivatives of the loss with respect to the output at time t, and the derivative of the output at time t with respect to the width WQH. But how can we calculate this? To make it easy, I brought up this formula from the previous slide. Taking the derivative of the output OT at time t with respect to the width WQH, what you have is just this. So that is here. And eventually you have the result for the first derivative, derivative of the loss with respect to the width WQH. Now we calculate the derivative of the loss with respect to the hidden state at the final time step t. Upper L, the loss, depends on the hidden state ht of the final time step t only through ot. So in order to see that, I go back to the visualization, and here the final time step is t equal to 3, and we could see the loss function depends on h3 through o3 only. So the derivative of the loss function with respect to the final hidden state h uppercase T follows the chain rule, and here we don't see the sum anymore. How can we calculate this derivative? Again, I brought up the formula from the previous slide for the output variable. Taking the derivative of OT with T at the final time step. Actually, T here is uppercase T at the final time step. With respect to the hidden state at the final time step, what you have left is just this, which is the width WQH, which is here. And finally, this is what we get for the derivative of the loss function with respect to the hidden state h uppercase T of the final time step. For other time steps T before the final time step, the loss function depends on the hidden state ht through ht plus 1 and ot. So to calculate the derivative of the loss with respect to the hidden state at time t, we apply the chain rule. Looking at this derivative, the hidden state at time t plus 1 gets contribution from the previous hidden state through the width matrix WHH. So taking this derivative, what you have left is just the width WHH. Now looking at the second derivative, we had this before here. And when you take the derivative of the output at time t with respect to the hidden state at time t, what you have left is just the width matrix WQH. So that's what we have here. So eventually, this is what you have with the derivative of the loss function with respect to the hidden state at time t. Looking at this formula, this is a recursive formula. The derivative of the loss with respect to the hidden state at time t depends on the derivative of the loss with respect to the hidden state at time t plus 1. So if we expand this recursive formula, what we get as the general formula for any time step between 1 and the final time step is this. Looking at the power, when the number of time steps uppercase T is very large, or other time step T is small, meaning the I here, this derivative is prone to vanishing and explosion unless the width WHH is very close to 1. In that case, when taking the power to the uppercase T minus I, the vanishing or the explosion of gradient do not happen. So then now we can calculate the derivative of the loss with other widths such as WHX and WHH. Now we apply the chain rule just similarly. The loss depends on WHX and WHH through the hidden states from H1 up to the final hidden state. And with that, you can go back to the visualization to see the loss function L here depends on the widths WHX and WHH via the hidden states. So apply the chain rule, and we have the sum for all the time steps from 1 to t, to uppercase T. Of the product of the derivatives. And again, I brought back this formula from the previous slide so that you can see how we get how we calculate this derivative. Taking the derivative of ht with respect to the width whx, what you get is just ht, and that is here. And eventually we have the sum from 1 to t of that term. And similarly, this derivative can be calculated when you take the derivative of ht with respect to whh, and what you have left is just this, and that is in here in the second derivative. And that's how we get the derivative of the loss with respect to whx and the derivative of the loss with respect to the width whh. How do we handle the case of exploding gradient during back-propagation? So there is a technique called gradient clipping. If the gradient is larger than some threshold, then clip it by just capping the gradient. Another approach is to not update all the widths in the way back, and this is called truncated back-propagation. This approach is not optimal because we don't update all the widths.